Hi, everyone. So I'm going to record a video about global climate change, give you an overview of this field. We're not going to talk about in class too much, but worth hearing about, and it'll help you with your homework assignments coming up. So what is this fuss about global climate change and what's going on here? So it's a pretty complicated field that rests on a couple of key scientific observations. Okay, so one is that if you think about how the Earth stays warm, of course, the Earth's proximity to the sun and the energy that the sun radiates is really important for this. But the Earth would actually probably be a frozen, well, it certainly wouldn't be so comfortable as it is now if the atmosphere of the Earth didn't have a way of trapping heat in some way, and that's called a greenhouse effect. And what that is essentially the atmosphere of the Earth helps keep some of the energy from some solar radiation that's incident upon it, helps keep that energy within the Earth's system, within the atmosphere. And that's basically by converting some of that energy from the sun into wavelengths of light, which actually cause molecules in the atmosphere to actually warm up, vibrate faster, move faster. So that's actually increasing temperature. And so basically when the sun radiates its energy, the light comes onto the Earth and it is incident on the Earth, and then some of it's absorbed by various surfaces. So the water absorbs some light, of course, and land surfaces absorb light, and plants on that surface absorb light and photosynthesize and carry on, right? And some of that light is actually reflected into space. Clouds, for example, which are white, of course, reflects space, light away from the Earth, and that would help cool it, right? Or the ice caps or snow fields reflect light from the sun and help cool the Earth, right? Now, some of that energy, as it's converted into other forms, becomes basically infrared radiation, and that's basically heat. And that radiation that energy is re-radiated back out into space from the surface of the Earth and through the atmosphere. And there are things called global greenhouse gases, which will absorb that energy, infrared energy, and then re-radiate it. And the more global greenhouse gases you have, the more that energy can be re-radiated back into the surface of the Earth, thus increasing the temperature of the Earth. So we have greenhouse gas in the atmosphere, which are mainly carbon dioxide and water. Water is actually the biggest one, but carbon dioxide is one that's most variable because of human activity. And those molecules will take that infrared energy that's bounced or radiated off the surface of the planet and absorbed by the atmosphere, absorbed by those molecules, water and CO2, and then re-radiate it. And some will be re-radiated back into space and it's lost, but some's re-radiated back onto the surface of the Earth, and it helps warm the surface. So that's called a greenhouse effect, right? Now, this can actually become quite extreme. So Venus, for example, is another planet. It's the next planet in towards the sun, and it has an atmosphere that is very thick and mostly just CO2, and it's extremely hot. That planet's surface is about 860 degrees Fahrenheit on the surface. It's extremely hot, and part of the reason is it's not only because it's closer to the sun, Venus is, but it's also because CO2 is the main component of the atmosphere, and that's purely a greenhouse gas. And so when that energy is radiated on Venus and then turned into infrared and then re-radiated, a lot of it's absorbed by the atmosphere of CO2 and then re-radiated back onto the surface. And that causes the atmosphere to really heat up. It's called a runaway greenhouse effect. And so it causes Venus to be very hot. The atmosphere of Earth has a very low CO2 content as opposed to that of Venus. And it's about 0.04% or so of the atmosphere pressure, right? Most of the atmosphere is nitrogen, N2, and oxygen is about 21%, nitrogen is about 80%, or a little less than 80%, right? And then like CO2 is a tiny amount, and then water vapor and some other things, right? And that tiny amount of CO2, though, is really important for regulating the temperature of the Earth because of the greenhouse effect, right? Okay, so what pattern that's been noticed over the past century or so is, about 50 years, 60 years, people have noticed this, but you can look at the data and see that there's a pattern emerging. That's, we'll talk about more about what that means. that humans have been burning fossil fuels and producing CO2 in large amounts since the industrialized age started. And the CO2s have been increasing. We've been measuring CO2 concentrations in various locations. Mauna Loa Observatory in Hawaii is the best known one. And here's since 1960, just a small subset of the data, but here's the CO2 increasing. It increases pretty steadily from year to year. This jagged line is because of winter in the northern hemisphere, where most of the plants live, tends to result in more CO2 being in the atmosphere. And then when spring happens and leaves start to leaf out on the northern hemisphere deciduous trees, we start absorbing a lot of CO2 from the atmosphere. So CO2 concentration goes down. And the next winter comes, it goes up again, down. But now it's on a steady path. If you smooth this, it's increasing amount. And the difference is that the CO2 is being produced as a result of burning fossil fuels around the planet. Okay, now if you look at the temperature trends, and these temperatures are measured probably directly by thermometer readings around the world. And what you see is that temperature roughly follows CO2 increase here, right? So it's natural to conclude that increase in CO2 is going to result in an increase in temperatures. And that fits well with how we understand CO2 works in an atmospheric setting, that absorbs infrared and re-radiates back towards the planet sometimes, and that causes the planet and the atmosphere to warm up, right? So fits a theory, right? So this actually makes a lot of sense, and is the foundation for global warming theory. All right. Okay. Now it's going to turn out to be a little bit more complicated than this because of the complexities of the Earth's climate system, right? But this is the basic theory. Okay, so one of these things that we should be aware of is I'm going to just mention that how do people really pay attention or predict what's happening with climate is this idea of climate change modeling or climate modeling. And basically what the idea is here is that you can take a computer, give it all sorts of variables about climate and all the equations and stuff to predict, to describe how CO2 and water vapor and so on works in the atmosphere as far as absorbing energy and re-radiating it. And you can develop a computer model that will simulate the climate, right? And there's a lot of people working on this. There's several climate models out there, right? And computer models are designed to post-dict, in other words, take data from the past or take the climate model and you input data from the past and get the climate model to show what the climate was back in the, before the computer model was actually built, and show that the climate actually did have those characteristics. So the computer model can actually kind of post-dict the climate at a historical time, right? That's a confirmation that the climate change model actually works. And then the climate change model will then, if it's working that way and can post-dict effectively, well, then it can predict global temperatures over time, right, in the future, based upon how much CO2 increases and what happens to other variables, right? It's pretty important. This is heavily used. You see it reported on a lot. A lot of climate change models are used to show that the Earth's going to warm X amount by 2100, so on. You hear all sorts of things in the news about this. And these are all basically based on climate models that have been tweaked or changed or updated and are cranking out new predictions about what the climate's going to do in the future, right? And you hear about these pop up every now and then, and they are often used to show that, okay, they're going to impact hurricane frequencies or tropical storm frequencies in the Pacific, or that the ice cap's going to melt, or the water temperatures are going to increase in a certain pattern, or rainfall pattern is going to change. So those are all based upon climate change modeling, right? And the more people work on these and develop them, the better they are in theory, right? Now, these are valuable, incredibly valuable for actually figuring out what's going on in climate, but they're not infallible. These are not, I should have two L's in it, sorry. These are not perfect, right? These are, they're models. They're not actual measurements. So these can actually be missing key variables. The variables aren't correct when entered into the model, and then the group and the output of the model is not accurate, right? This is a tricky part about computer modeling. It seems like it's a pretty tight way of measuring climate change, but it actually is not perfect. Valuable, but not perfect. Keep that in mind. I'm going to show you here a GISS climate model. It's from NASA, that the model they use, and how they predict how they post-dict the climate, the model of the Earth's climate in the past, since about 1850, or even older than that, all the way up to like 2100, something like that. I'm not sure how far. So let's look at this and see how this works. All right. Okay. So hang on just a second. Let's load this up. Okay, here we go. It's only 36 seconds. Okay, here we go. All right, so we're going to start at, we'll get back to the beginning. Okay, we're going to start at time. Let's start. Okay, well, let's just start up running. And then it's 5-year intervals. What they're doing is they're modeling the model of the climate every year, and then taking 5-year intervals and averaging them out to give you kind of a prediction of what temperatures will be in different parts of the planet. Right. So here we go. We're going to start at 1885. Okay, so that's where it starts. You can see the blue is cooler, reds and yellows are warmer, whites are kind of neutral, right? So this is kind of relative to today, I think, temperatures, right? And so you can see over time that the climate going in later times, it's getting warmer and warmer. And this is the climate model based upon the amount of CO2 being put in the atmosphere and how much is in there. We know about, now we're going to the future here. See that, right? So they're predicting now that the model is going to, that the Earth's going to warm up in this particular pattern, right? All the way up to 20, let's see, looks like it's 2100. Yeah, okay. So let's do this again, all right? And I'm gonna pause it. All right, now, so blues are cooler, right, than today. Warm, yellows and oranges are warmer, right? You can see that the warming, the climate is not, this is basically, I think this is actually a measure of anomaly. This is actually the difference from what the climate's like today, or some average of what the climate was like in modern times, like last 10 or 20 years, right? Versus what it was in the past. So these changes here are that the climate in these areas that are blue was cooler in the past, right? And these climate areas in yellow and red and browns are warmer than they were now. Okay, so in the past they're a little bit warmer here than they are now, or they will change. Well, they'll basically fluctuate. You'll see, right? Now notice that the climate is not. These are not. Climate change is not even. Some parts warm up faster than others, and some parts they actually stay cool or cool a little bit as climate warms. But overall, the climate is going to increase according to this model. So let's keep it running. So here we go over time. You can see basically it's uneven warming, right? But it's slowly getting warmer, right? The yellows are getting more and more dominant. Blues are getting less and less dominant, right? Okay, so let me start at 2020. Here it comes. All right, right around here. Okay, so a little too far. Let's go back just a tad. Okay, close enough. All right. So now, based upon whatever the starting point was, I guess their starting point wasn't probably modern times. It must have been starting point of sometime in the mid 20th century. Anyway, so you can see some areas, it's a little bit cooler here off of Greenland, according to the climate model, but you can see the Arctic tends to be really much warmer, right? And certain parts of Africa and Asia are in North America are significantly warmer. Right, so climate change is not uniform. It's unevenly distributed throughout the planet. That's basically because of the way the climate works on our planet and how it distributes heat. Let's continue running this. And the warming really increases rapidly. Right now we're starting to get these dark reds, right? Practically browns. Those are super hot. So the relative to normal what we consider normal temperatures up here, right? So the Arctic's going to really fry. And so is our Africa, okay? So those are things that climate change modeling allows you to kind of predict, right? And think about. And the post-diction idea is that, again, you can take this model, run it with past data, and get it to show a model that actually felt relatively accurate for what we know.
Yes, this has shown us that ours is a precious
Whoops.
planet.
Sorry, hang on. Stop this. Okay. All right. So, okay. So that's climate change. Now, there's some things you need to think about when you talk about climate change also. There's lots of ways to measure the Earth's temperature. You should be aware of this, right? Obviously, you could well, okay. So the measuring temperature on the Earth is actually complicated, right? You have to have instruments or ways of measuring. They're in different locations at different times over the surface of the Earth, and they're different methods. So you got to find a way to actually match them to and make them make sense for a overall temperature of the Earth, right? So some of this is going to be thermometers on the surface, like a weather station located at some particular location. In fact, we have one on Gelb that's not functioning right now, but did for a while, right? And then you can have satellites measuring temperature from space. And then you can have different things. You can measure plant growth is a way of measuring temperature, right? Tree rings, so on and so forth, right? So these are different ways of doing this. And this is actually fairly complicated, takes a lot of work, right? There's a couple of things you should be aware of. You may have heard of things called climate forcing. And this is a idea that there's factors that cause temperature change on Earth over long time spans. So examples of that include solar radiation, right? So the amount of solar radiation incident on the Earth, it will cause it to have a certain temperature, right? That's a forcing. So there's a solar radiation forcing. If that solar radiation increases, the forcing increases. If the solar radiation decreases, the forcing decreases, right? Greenhouse gases are force. It causes a forcing. So increasing greenhouse forcing will increase the temperature. Decreased in greenhouse gas will decrease greenhouse gas forcing and cause the overall temperature to decrease, right? So forcings are just basically these contributing factors to climate change or warming, all right, or temperature. All right, then proxies is another term you're going to hear a lot about, right? And these are ways of measuring temperature that don't necessarily rely on the use of thermometer or direct measurement of heat, right? So there are a lot of proxies. These you use a lot, and especially in times where we didn't have instruments to measure temperature, before the invention of the thermometer, right? We would have to figure out temperatures using other methods. And there are ways of doing it. Tree ring, I mentioned one, like tree ring growth is one way of measuring temperatures in the past, because the tree rings tend to be wider when it's warmer and narrower when it's cooler, although that's variable based upon it could be water resources in the soil and so forth will influence tree ring growth too. So it's a little more complicated, but you can basically get an idea for temperatures based upon tree rings, how well they grow, the trees grow. Oxygen isotopes and the isotope ratios of oxygen isotopes can help determine temperature. You have more heavy isotopes when it's cooler. I don't remember. I think that's right, and then less when it's warmer. Anyway, you can figure this out, and you get different temperatures based upon isotope ratios. And this you can actually measure, because you can actually find oxygen from air in the past. Let's say in an ice core, in a glacier or something that goes way back in time. You can do an ice core and then measure the oxygen isotopes in that core and find what the temperature was at that time based upon these ratios. Pretty nice. Okay, and you get data like this, right? So over time, you get these measurements of temperature, and then this is the orange line here is just an average, like a running average, 3-year running average or something, right? And you measure the temperature, and an anomaly is relative to some time, like I don't know what the anomaly measurement key is here. It's like maybe like 1950 or something like that is a set point for when temperature was average, like what the Earth's supposed to be, kind of, right? And so what you find is that the temperature was lower in 1850 or so, and as humans pumped out more CO2 or did something, the temperature increased over time. And now this is a little not completely to where we are now. You can see there's a trend in temperature going up. Now it's not even, and it jumps around a lot, and some years are warm and some years are cold and whatever, right? But there's a trend, overall trend, which is increase. All right. Okay, so it looks pretty well, like temperatures really increasing over the past century or so, century and a half. All right, now here's what the data looks like. This is using satellites measuring temperature since 1979. And satellites are essentially measuring more or less directly temperatures, right, of the Earth, the whole Earth, right? Satellites orbiting the whole Earth and measuring basically how much infrared radiation is radiating off the planet, right? And you can see since 1979, again, the temperatures have been increasing, right? They're going up, but they're really going all over the place. Like they bounce around, they kind of plateau in areas, and they peak up, and then they plateau, and they peak, and they plateau, and then peak again, plateau, peak. All right. Now these peaks tend to be correlate with certain climatic events. These are El Ninos. These are when the Pacific warms up around the equator and gets really hot, and it puts off a lot of heat, and it warms the atmosphere. And then it cools off after that, and to an El Nino or something like that, and you get these overall. So look where we are now. Like March 2021, the temperature is actually below the average temperature, which is 19 whatever year the average is. Maybe they took it for 2005 or something like that. Okay. All right. So that's the average year. And this is again anomaly, the amount of temperature difference between the average and what it is when you're measuring. Right. Okay. So it's actually cooled off, and we had a big El Nino 2019, and now that's cooled off, and the temperatures dropped down. Now the running average, of course, is not caught up to this yet, because it's a 13-month running average, right? So this is a little bit behind. But this is 2021. Here's March, right? And so you can see this. This is a satellite measurement, right? Yeah, the temperatures are warming, but unevenly. Okay. All right. Now, how's this match with CO2 increases? Well, look at this. So here's our measurement. This is with instruments, I think, measuring temperatures since 1956 or something like that. And you can see that temperatures have been increasing, but they don't match with CO2 increases. So CO2 increases from Mauna Loa look very kind of smooth, right? Kind of exponential, actually, right? But look at the temperatures. In the 1950s, the temperature was actually coming down off of World War II, actually. 1940s was temperature peaked before it started cooling for some reason. We don't really know why, but the temperature started cooling on the Earth down in the 1970s, and then started increasing again through the 1980s and into the 2000s. And it cooled a while in the plateaued kind of in the 2000s, right? And then started increasing again, right? And we had a couple big El Ninos here, right? So they really warmed up. Here's March 2021, so down again a little bit, right? Now, what this is showing here is the correlation with CO2 increases. There's a negative correlation with CO2 increase here. See that? The CO2 is increasing, but the temperatures have been going down. So that is not showing that CO2 increases uniformly increases the temperature of the Earth. It's not that simple, right? That's a negative correlation. There's some other forcing happening here that's cooling the Earth, maybe that's overriding this, right? And then there's a period in here where it kind of matches, right? Temperatures increasing with the CO2 increase, but then it decouples again, right? So here, we got a little bit of plateau, and then an increase, and then a little more plateau, and CO2 is still increasing rapidly. So if this was a perfect match, right, temperature of the CO2 and just increase just the same way, you'd think, okay, that's actually pretty strong, that there's not, CO2 is the main force in here. But obviously it's more complicated than that. This is a little bit more wacky and not so simple. So what I'm saying to you is not that CO2 is not causing global climate change or anything. What I'm saying is that the data is a little bit more complicated than you hear about, and you need to be aware of that and thinking about what's going on here. There's other things, other forcings, like what made it cool here? It is pollution, right? A lot of sulfur dioxide being pushed in the atmosphere. And then we start cleaning up our act in here. And then the solar radiation incident on the Earth increased because the pollution went down, right? And then we start seeing more temperature increase because of CO2, right? And then something else happens here that's decoupled that again. We don't know, right? So this is why climate change is such an important field of study to figure this stuff out. Okay, I'm going to stop here and start another video. The one I just showed you, this part should help you with your homework coming up.